Last month, a backyard telescope in Austria captured an image of 3I Atlas that is sharper than anything NASA has shown the public. Jets, structure, a sun-facing plume of material that shouldn't be this obvious. And yet, in the official gallery, those details are barely there. So why are people with telescopes in their gardens seeing a comet that doesn't quite match the one NASA is showing to the world? There's a persistent jet pointing toward the sun, a retrograde orbit that still hugs the ecliptic, and gaps in the public image record that no one has fully explained. Suddenly, the quiet frames from amateurs feel more revealing than the polished images in press kits. What exactly are we missing? And why? On a clear July night in Austria, Michael Jaeger rolled out his 11-inch Newtonian telescope and pointed it toward what, to the naked eye, looked like nothing. Just a faint blur in the star field. The blur had a name, 3I Atlas, and Jaeger had a plan. He cooled his CMOS camera to cut noise, then shot 45 one-minute exposures, each one registered on the comet's slowly drifting nucleus, rather than the stars. Individually, the frames looked unremarkable, but stacked together, they revealed something different. A crisp, bright core. A coma with visible structure, not just a uniform glow. A tail that split cleanly from the nucleus, with geometry instead of just fuzz. Within hours, that image spread across astronomy forums. People began posting side-by-side comparisons. Jaeger's composite versus NASA's official images of 3I Atlas, where the institutional frames looked soft and evenly lit, perfect for a press release. The amateur composite showed sharp contrasts, layered structure, and a clearly defined tail. And Jaeger wasn't alone. Across Europe, North America, and South America, a loose global network of hobbyists fell into the same nightly routine. They registered each frame on the comet's nucleus. They discarded any exposure with trailing or distortions. They stacked dozens, sometimes hundreds of images. Then they applied rotational gradient filters and unsharp masking to tease faint jets out of the glow and sharpen boundaries in the coma. In France, François Coquel shared his process. A line on the core, stretch the histogram just enough to bring out faint structures, then gently sharpen outflows. In India, Vamshi Kesarati described a similar workflow using Deep Sky Stacker, pics in sight, and final tweaks in Photoshop, or with open-source scripts, different continents, different setups. Same pattern. When their images were placed next to NASA's public gallery, the difference was striking. Official images looked smooth, aesthetically pleasing, softly lit. Amateur stacks revealed jets, texture, sharp transitions, a tail that clearly emerges from the nucleus. One observer joked, "If NASA won't show it, I guess it's up to us." Others were less amused. They pointed out that in a single night, with a modest telescope and transparent processing, they could reveal core features that simply didn't appear in any public gallery from the world's most powerful space agency. Whether NASA had those details internally wasn't the issue. The real question was, why weren't they in what the world was allowed to see? In that gap, the role of the amateur began to shift. The stacking community didn't just fill in missing pixels. They became witnesses, showing that with patience and open methods, even a backyard instrument could reveal what billion-dollar observatories sometimes left in the background. For more and more people watching 3I Atlas, the sharpest window wasn't in an institutional archive. It was on a laptop, in a dark backyard, beside a telescope that someone had built and tuned themselves. The most debated feature in these amateur images is also the hardest to ignore: a forward-facing jet. An arc of material that appears to blaze ahead of 3I Atlas, toward the sun. One strange frame could be a stacking artifact. One odd shape could be blamed on software or optics. But that's not what happened. Over weeks, independent stacks from Austria, Chile, North America, and beyond all showed the same sunward fan. Bright, persistent, sometimes shifting slightly with the comet's rotation, but never disappearing. In technical threads, observers measured the jet's angle, traced its length, and compared it to the comet's motion and changing orientation to the sun. Their conclusion was simple. This structure is real, not a glitch. not a one-off outburst. The puzzle gets deeper when you place that jet on top of the orbit. 3I Atlas moves on a retrograde path, going against the direction of most planets. Retrograde motion for interstellar visitors isn't shocking by itself, but 3I Atlas adds a twist. Its trajectory still hugs the ecliptic, the thin plane where most of the solar system's mass orbits. According to late 2025 JPL Solutions, its inclination sits near 60 degrees. That's steep, but not wildly tilted, not plunging in from a random angle. Instead, it's an interstellar object moving against the flow while skimming close to the solar system's main plane. Orbit modelers at NASA and the Minor Planet Center flagged this combination as rare. Internal comments reportedly called it one for the textbooks, noting that most interstellar objects are expected to arrive from more extreme angles. Then there's the jet. In most comets, jets erupt from active regions on the surface. They rotate in and out of view, flicker, and fan out as the nucleus spins. But in 3I Atlas, the sunward jet stays anchored for weeks, roughly aligned with the direction of solar heating, suggesting a patch of highly volatile ices recently exposed and facing the sun. Some professionals argue this can happen during a comet's early, intense heating phase, but the persistence across nights, telescopes, and observers keeps the mystery alive. On paper, it's still just a comet. In practice, it's a pattern that doesn't fit comfortably inside existing models. The orbit teams can map the path. What's harder to map is the history and the process that created this combination. Retrograde, near the ecliptic, interstellar, and showing a stubborn sunward jet. As one planetary scientist put it, we're seeing something that feels ordinary and statistically unlikely at the same time. 3I Atlas isn't alone in pushing the edges of what feels normal. See 2014 UN 271 Bernardinelli Bernstein came from deep within our own system, from the distant Oort cloud, but it challenged expectations in a different way. It first surfaced in archival survey data, not a new discovery image. Buried in those old frames was something enormous, a comet roughly 150 kilometers across, confirmed by Hubble and ALMA. Most long-period comets are tiny beside it. UN 271 rivals the icy bodies of the Kuiper Belt, and it didn't wait to get close to the Sun. In 2014, at nearly 24 astronomical units away, far beyond Saturn, astronomers detected a faint coma around it. By 2021, still more than 19 AU out, radio telescopes measured carbon monoxide streaming away at a rate close to 5 times 10 to the 28th molecules per second. ALMA and the James Webb Space Telescope revealed a mix of super volatile ices, carbon monoxide, carbon dioxide, ammonia, escaping from a surface that should have been frozen solid. Standard models allowed for the occasional distant outburst, but UN 271 showed sustained activity over years and vast distances, implying a huge reservoir of volatile material preserved since the solar system's earliest days. No one disputed one core fact: no comet had behaved like this before. UN 271 forced scientists to stretch their ideas of what comets can do in the deep cold. 3I Atlas is now forcing them to stretch what interstellar visitors can look like inside the solar system. In less than a decade, the solar system has seen 3 confirmed interstellar visitors. Oumuamua in 2017, tumbling, elongated, with a puzzling acceleration that still fuels debate. Was it a shard of something larger? A fragment of a disrupted world? Something else entirely? Borisov in 2019, a more classical-looking comet, but with a composition that raised its own questions about how material from other systems compares to our own. And now 3I Atlas, with its retrograde orbit near the ecliptic, a persistent sunward jet, and a visual story that looks one way in amateur stacks and another way in official releases. This clustering is hard to ignore. For centuries, whole generations of sky watchers lived and died without a single confirmed interstellar visitor. Papers published as recently as 2015 still estimated that such objects might be found once per century, not 3 times in under 10 years. Some survey scientists say the explanation is Simple. We've finally turned on the right lights. Wide field searches like Pan-STARRS, the Zwicky Transient Facility, and soon the Vera Rubin Observatory scan huge swaths of sky every night, catching objects that would have slipped past unnoticed before. Others suggest something deeper. Perhaps the space around our system is more crowded with interstellar debris than we assumed, and we're only now seeing the true background. Inside observatories, that debate happens in data rooms and equations. Outside, the tension takes another form. On social media, in forums, and in YouTube comments, another question keeps returning. If our instruments are this good, why does the clearest view so often come from a garage or a garden? Citizen advocates and science communicators point to the contrast. Backyard stacks that show jets, structure, and sharp details in near real time. Official images that sometimes appear softened, delayed, or incomplete, especially when the story gets strange. The loudest voices aren't calling conspiracy. They're asking for raw, unfiltered data. They want to see what the telescopes see, not just what fits neatly into a press release. For every new visitor, Oumuamua, Borisov, 3i, Atlas, the gap between what is quietly observed and what is immediately shared seems a little wider. The stakes have moved beyond a single comet or a single press image. They become questions of trust. Who gets to witness the universe as it really is? Who decides which features are too messy, too uncertain, or too confusing to show? And what happens to public confidence when the sharpest images come from people working in the dark, outside the institutions? Right now, some of the most intriguing mysteries in our skies aren't locked away. They're simply understated, left in footnotes, smoothed out in galleries, or revealed first by people whose observatories have no front gate. As new visitors cross the solar system, public trust won't be built on perfect narratives. It will depend on clarity, completeness, and honesty. Even when the data refuses to fit the models, the cosmos isn't waiting for anyone to be ready. It sends objects through our neighborhood on its own schedule. We can wait for official summaries, or we can look where the light already is, on stacked frames, open archives, and the raw, restless curiosity of people who refuse to look away. What stands unexplained today doesn't just haunt our curiosity. It shapes how we'll remember this moment, not just as the time the sky got strange, but as the moment we chose either to smooth it over or to finally look at everything it was trying to show us. In Cosmos, we trust